Okay, I think we'll go ahead and get started. I hope everybody has a lot of energy and ready to finish this day strong. We have one last session to get through, and I think it may be a short one, since I think we have a couple of no-shows here, or I think at this point we're down to 2 speakers for this session, so we'll see how it goes. Maybe they'll still show. So this is the session T2S2, Space Technology and Data for Water Quality Monitoring. Our first speaker today, the title is Uncertainties While Classifying Cyanobacterial and Microalgae Blooms. Francisco Namina from CANE. Francisco is a physicist student who has been working on the CANE on ocean color and water quality topics for the last 8 years. Currently is focusing on uncertainties of water quality indicators provided by remotely sensed data. So, Francisco.
Sorry about you. Well, hello. My name is Francisco. I'm from CONA in Argentina. And my idea for... That's me. I will do 2 shows. That was the first one. The idea for today is to speak a little bit about hyperspectral data and how we can use it to classify cyanobacteria and algae blooms. This is an image for San Roque Reservoir in Córdoba, Argentina, taken by the Prisma satellite by the ASI, the Italian Space Agency. And it's a nice satellite. It has several bands, especially in the visible. We have 66 bands that are less than 12 nanometers width. And what we've been trying to do is to say, okay, I got this hyperspectral data for my lake. I want to identify what kind of bloom I'm having on the lake. So what I say is, okay, I will treat this as a spectral and mixing problem. I will have some water, some bloom. When my satellite measures, it's all averaged over that zone. But then I want to say, okay, my sample is a linear combination of the different algae I can have in my reservoir. And I will work backwards to get the fraction of each spectra, the fraction of each species of cyanobacteria or algae, and the concentration. Yes, I want to go backwards and recuperate something that has to do with my mix in reality and not what my satellite measured. And to do this, what we do is we try to minimize a distance function. There are several to do this. You got the Euclidean distance that it's here, but you also got the spectral angle, the NS3. You got tons of things you can minimize to get your values that, okay, this is my linear combination. And when you do that, you get a result. So it was going to be short. You get, okay, I got that most of the lake has no cyanobacteria. It has Cryptophyta, that is another species. And then in the middle, where I had the green part, I got cyanobacteria. This is what we expected for the lake because we know it. We know that it has blooms every once in a while that are pretty big with concentrations over 500 milligrams per cubic meter of chlorophyll. So it's good. But then it comes a problem here is, okay, but your satellite has a problem. The measurement from your satellite is not perfect. Your atmospheric correction algorithm is not perfect. Your spectra to do the unmixing are not perfect. So you got uncertainties all over the place. And I like this quote from Juan Herrera. He's an Argentinian physicist that when he spoke about measuring, he said that if you measure several times, you will have several results. especially if you drink wine between one measure and the next. I didn't drink anything here, but there is this thing, okay, if the satellite comes again and measures again, will I have the same result? Can I trust this result? And this is where the travel starts. This is what I wanted to really talk about. That is, okay, how can I say something about my degree of trust with these results? And how can I quantify the errors I'm committing in this spectral and mixing from the satellite, from the spectra in the field, from everything, yes? To do this, we did some simulations. First, we started with generating water reflectances using hydrolite to get members. Then we got the top of the atmosphere reflectance using T2S to get what the satellite would have measured. Then using the Acolyte software, we did the atmospheric corrections and we knew our input, and now we can try to get our output. We do the unmixing, yes. So we can compare, okay, I put this input into my system, half cyanobacteria, half not cyanobacteria, and I got this output into my system. And I can say, okay, I got more noise in the satellite. I got 0.5%, 1%, 2% of error at top of the atmosphere. And I got this atmospheric correction algorithm. And then I say, okay, I got this error in the fraction of each one. To do this, we did some hypothesis testing and used the name and bell construct to try to get these values. And here I'm missing something. Okay, you have to imagine something here that you have two distributions. One will be over here. That is the distribution for, okay, my result is right. What I put for input is what I got for output. And the other one is over here that is not right. And using this, you can do hypothesis testing and say, okay, if I want 66%, 68% of my data to be in my confidence interval, then this is my threshold. If I want 95, this is my threshold. If I want 97, this is my threshold for the Euclidean distance that we are talking about. We can calculate this for different uncertainties for the top of the atmosphere reflectance. And then we have a criteria to say, okay, if you did the unmixing and the distance, the Euclidean distance is less than this value, you can say the unmixing is good. And if you did the unmixing and the Euclidean distance is greater than this value, don't trust this. This is not good. And you can say it with different confidence levels. And you can also say here, you have to use your imagination. It will be better here. You can define the confidence interval for the fraction that you have. So if you measure with this uncorrected algorithm here, and your value was 0.4 for the fraction of cyanobacteria, then your plus minus is 0.15. Yes, you are in that interval. And if you correct it a little bit more, you can do the same here and say, okay, my interval is plus minus 0.5. That's the right kind of things we are trying to do. You got a pixel, you get uncertainty, you get how confident you are in that result. And we can now do that. Yes, this was the classification. Yes, that we got here for the cyanobacteria and here for no cyanobacteria. And you can see that if we put the cutoff values that we got before, it's not good. Yes, with a confidence level of 1 sigma, nothing in the leg was well classified. So this is really nice, but the truth is you don't have to trust this. If you go with a confidence level of 2 sigma, then, okay, this part of the leg seems good, but the rest of the leg is not good. Yes, you have to keep working. And if you go to 3 sigma and you are quite of stretching it, you can say, okay, you got more of the leg, but this is not among your spectra. Your mixing that you did is not right, even though you got a result that looks right, yes? So you can do the same to get the uncertainty for everything. And this is the kind of problems that I believe sometimes we hide under the rug, that we don't talk about, that we got the classification, it's good, but this classification could have been done for the leg with a road and trace, and you will have had a result. And it's not a good result, because when you go, you do the statistics, you do everything, per pixel, you can say, okay, this is not good, this is not good, this is not good. How do we improve this? We can. And to improve this, the first thing we need is more in situ data. These kind of a mixing algorithm are really sensible to the end members that you have. If you have race and roads, you will do one mixing and it will be bad. But if you have the specific species that you have in your lake, then you will get a lot of better result. The problem is then you have to measure in your lake absorption coefficient, backscattering coefficient, everything. And it's for one lake. You want to do it for everyone. So we can do this. We can perform these in situ measurements, but we have to be careful. We have to get the in situ data for our results to really match what we expect, even though the initial result might look good. Yes, this is everything I wanted to talk about. I work in this group at CONAE, at Instituto Gulich. They do a lot of water quality parameters, data. You got people working in snow, in algae blooms, in hyperspectral, in lots of stuff. So any question, you can ask it. And thank you.
Questions from the floor? Yes, sir.
I'm Jad Ali from Sparko, Pakistan. My question is more toward the methodology which you have adopted in this particular study. My question is targeted toward the selection of the technique which you have used. You used Euclidean distance. But do you have any particular reason for not using the new technique like convolution neural network or the random forest technique, because they are also giving promising results in complex data context?
The idea here was I use Euclidean distance because I thought everyone will know it. So it's easier to imagine that you're minimizing the distance. We tried two more. We tried a spectral angle mapper, and we tried NS3, that it's a mix of spectral distance and spectral angle mapper. In the future, we want to try more techniques, but our main focus is not on the unmixing. A lot of people are doing that and are doing it quite right, but on how you can generate uncertainties for the mixing with the data you have from your satellite. So we could have done random forest, and we would have had results, and then the same analysis would have to be done. In random forest, I guess you will also get a result. And always the idea is, okay, now go back and say something about this result, about the statistics of this.
Other questions?
Distinguido, ¿cuál es la diferencia entre una criptobacteria y una cianobacteria?
What is the difference between a cryptobacteria and a normal cyanobacteria?
Yes. The question is, what's the difference between cyanobacteria and cryptophytes? In this work, I only used two species of phytoplankton. We are really interested in cyanobacteria because they are toxic and they are present in our lake. And San Roque Reservoir is the drinking source for Córdoba City that has 2 million inhabitants. So it's important to say, okay, you can use this water or you have to treat it in another way, and to see how it evolves in time. For this work, we choose Cryptophyta because it's present in the lake and it gives the best results. But you could do it with tons of species, and each lake, each reservoir will have their unique phytoplankton flora, and you'll have to do it for your lake or reservoir or whatever.
Yeah.
Well, thank you for your presentation. This is Mandita. Yeah, I was wondering whether there's any kind of threshold or limitation in terms of the size of the lake or the water body that can detect these, bacterias.
Okay, the limitation is more on the spatial part of this. Currently, that I know of, you have 3 hyperspectral sensors. You have Prisma from ASI, you have NMAP from the German Space Agency. They are both 30-meter resolution, so a lake of San Roque Lake is 2 kilometers by 5 kilometers, and you can do it there. Then in the last few months, you have Prisma. Prisma is from the NASA. It has a 1 kilometer resolution. The main difference between Prisma and NMAP and PACE, is that PACE is 1 kilometer, but it's functional. You get data every 2 days. Prisma and NMAP, you have to ask for it, and you have a temporal resolution of 1 month. So it's not so good data. It's good for research, and they have done tons of things. But if you want to implement something that runs every day, you will have to go to PACE, and PACE is 1 kilometer resolution. So for San Roque Lake, it wouldn't be so good. So the satellite PACE is 1 kilometer resolution. So your reservoir, your lake will have to be 5 by 5, 10 by 10 kilometers. It will have to be larger. In the next few years, there are going to be tons of new hyperspectral satellites. I know NASA has 1 in the making. I know ESA has 2. So there will be more data to do this, but currently this is our limitations.
Yes, thank you. Yeah, the PACE mission was just launched in February, and NASA right now is releasing the funding for the research that goes into PACE for, in particular, water quality. Over the next 2 years, it's going to be $9 million spent just on the research to work on the algorithm development, et cetera. Just a quick follow-up. Again, you mentioned there was 2 species or genera that you were using here. Did you know a priori that's what was in the lake? And if it was a soup, of 10 species, how would that complexity be handled, or was it just a multivariate equation?
Okay, for the lake, what we know is that in general, you have one or the other dominant. When you have blooms, you always have some of the other species. So maybe you have, I don't know, 5 milligrams per cubic meter of Cryptophyta, but then you have 200, 300 milligrams per cubic meter of Cyanophyta. And then it's like one is always dominating over the others. We didn't do this, but the Córdoba Hydrological Department did some measurements separating species in the microscope. And in general, you have like 10% of one species and the other 20% is divided among 10, 20 species different in the lake.
Okay, anything else from the floor or online? If not, we'll move on. Thank you very much. So the second one listed here, I don't think has showed up online, and we don't have a presentation for the talk from Sri Lanka. So we'll move on to, and I'm not sure, is David Zamora here? Oh, there he is. Okay, great. So our next speaker, David Zamora, is a civil engineer with experience in evaluating hydroclimatological effects related to land use and land cover transformations with the eco-hydrological approach, pollutants detection through continuous measurement technologies, and machine learning methods, water and soil resource management. And today he's going to talk about separate land use, land cover, and hydroclimatic effects on cyanobacterial harmful algal blooms in Weha Lake. Is that correct? Okay, thank you.
Thank you so much, and apologize for my voice. I try to do. My name is David Zamora. I am civil engineer. I work with SEI, Stockholm Environment Institute. Today I go to show some results about the algal blooms in Weha Lake. This is the content of my presentation. We had some context about what happened in Weha Lake related with different use of land and different hydroclimatic effects, materials and methods related with the input information related with in situ data and image from remote sensing. And after I try to explain cause and effects related with algal blooms, preliminary results, and some conclusions about it. This is Weha Lake. This is Weha Lake. It's a transboundary basin located between Guatemala, Honduras, and El Salvador. It has several sub-basins like Ostura River, Anguilla River, Lempa Alto River, and the other ones like Usmapa and Wajon. Yeah, is related with dynamics in Weha Lake. So you can find the main streams that discharge the water inside of this lake. And this basin has several crops, different kind of different quantity of populations in these basins. And nowadays, we have several causes or sources can affect the water quality in this lake. But in several media, you can find different news that say you what happened with chlorophylla, yeah, and different algal blooms. And for example, here you can see the news about the relation with volcano activity, with different feature activity and gold mine event, and maybe used on other kind of media like Facebook to communicate what happened with the Weha Lake, and finally produce the effects on the ecosystem, like several deaths of fish in this lake. So in materials and methods, we use the spectrometry to try to identify different dynamics in terms of water quality. But when I think in water and swamp, I remember the Pink Floyd album Music, yeah, and 3 songs for this album. The first is Time, the second is Money, and Are You Color Like? that is very related with dynamics of we have in this lake. In the first kind of time, try to represent different dynamics of land use that can affect by runoff with a lot of different kind of pollutant. In the case, for example, of crops, you can find different nutrients like nitrogen and phosphorus that can introduce elements or pollutants to increase the algal bloom presence. But we have a problem with money because in tropical area, even in Latin America, we don't have a lot of information for in situ data, for example, chlorophyll, TSS, COD, BOD. And these elements can to say what happened with the water quality dynamics. So you try to identify with these samples different behavior of the water quality, but the limitation of number of measurements are high. Are hard with respect with another kind of information and weak ability to identify the cause and effect. So we need to another kind of alternative source of information. In this case, we use the non-invasive measurements like satellite of drones to identify different elements in the spectra are related with the presence of different kind of parameters of water quality, and after that try to identify what happened around the lake. So in the materials you can see here two missions from Landsat 7 and Landsat 8, their availability data, in situ data in blue color. We have a lot of information, but we have a limitation in terms of parameters. We can find, in this case, the blue line represent all chlorophyll data, but we don't have all data related with nutrients like phosphorus and nitrogen that very related with algal blooms. And in this map, you can see the different points that are monitoring by different environmental authorities in Honduras, El Salvador, and Guatemala. And we collect this information from this time period from 2006, sorry, for 2023. Yeah, but we select just this time period because we have a more relation between image from the satellite to the samples. We don't have a specific information for the image to related with in situ data, so it's a high limitations for our analysis. And after that, this is the algorithm. It's very simple. You can use a linear data in lake. We use the satellite image. And after that, you relate different bands for the image to calibrate the linear regression. And after that, to elaborate the spatial distribution of the chlorophyll A. And after that, we try to identify what happened with different kind of patterns of precipitation in the year. And are there some significant changes in the precipitation that can affect or increase the presence of chlorophyll A in the lake? And in this case, we use the standard precipitation index to try to identify some tendency in this variable using the Mankendal test. So the question is, could the precipitation be decreasing and with this increase the concentration of some pollutants in the Ouija Lake? So to explore this question, we start to identify the main crops in this basin that we can see the 30% of area are related with agriculture, and we can find the principal crops, kind of crops in this area. You can see, for example, in the upper Lempa River, related with coffee and other kinds for melon or even for some grains. Yeah, and we try to identify what happened in the time. So I explain more about it after. But here we have the main data from in situ samples and measurements for some in situ proof. Here we can find the chlorophyll A, turbidity, and blue-green alga. Yeah, and you can find some correlation between these variables to identify what happened in terms of the increase or the decrease is the concentration of these parameters. And we can split the information into elements, into season, in dry season and wet season, to start to calibrate different kind of regression models, linear regression models, to combine different kinds of bands in the spectra. And after that, you get the correlate the coefficient of termination. Yeah, in this case, this algorithm was very interesting because gives a inverse relation between the between the band rate with the chlorophyll A. So we evaluate another parameters, but in this case, we use this equation. So with this equation, well, in this case is for wet period. In this case, we have a lot of clowns, and we can have a very poor correlations and coefficient of determination. So we select, in this case, this equation to represent the dynamics of chlorophyll in both seasons. And this is the result. Here you can see 2006 to 2023. And here for dry period, we can find here a good results in terms of performance to represent the chlorophyll, but we can find several problems in other moments because we don't have a match between a satellite image with the chlorophyll data in situ, and worse in the wet period. I know it's about results, but the indices of spectral indices help you to identify what happened around the Wihale, and with this equation, we represent in the space what happened in each moment of the year and related with precipitation. We can find, for example, in December, the high moment to presence of chlorophyll. We have in this moment less water and decrease the level in the lake. So it's most probably to increase the nutrient in the column of water. So, but in the case of a moment with more precipitation, we have more runoff and stream flow to inside the lake. So can you reduce the presence of chlorophyll, for example, in May? We estimate for another for each sample, yeah, and establish the dynamics around the year. But after that, we start to evaluate the trends of precipitation. Here you can see the monthly demand of water. Here the monthly precipitation of the year, and you can start to see here what happened in terms of trends of SPI. Yeah, in this case, we analyze just the trend with significant trend. That means the Mankendal was less than the alpha value, so the p-value is less than 0.05. And just in this area, you can find the precipitation are increased, and you can identify this is here in the lake, and several of this area that gives a lot of runoff and to the lake is increasing nowadays. And the other evaluation is evaluate the trend of vegetative production using NDVI to 2000 to 2020. Here you can see the main kind of crops like coffee, like grains, like vegetables and tomato and melon. These crops are present, increase the production. In this case, the more interesting is here the melon and the coffee. Coffee is a very important crop because it use a lot of nutrients. Yeah, and for in the river Ostua, arrive a lot of nutrients. Nowadays, we can try to connect the precipitation, the spectral indices, and the vegetative production to identify what is the main reason or are several reasons to algal blooms in the Ouija Lake. So for conclusions, high heterogeneity of water quality information limits the spatialization of chlorophylla. The information that we can find from different environmental authorities was very different in terms of quantity and spatial representation, but is helpful to identify areas of lake that where monitoring should be prioritized. Yeah, because more than the exact value, you give us some recommendation for environmental authorities to give more money to improve the monitoring. Give us some ideas to explore other drivers around the lake, such water quality, the algal bloom, and its ecosystems. For example, in the case of fishery, is need to explore more in a deeper way, because they have a lot of feature area around the lake. And although the reduction of precipitation is a hydroclimatic factor, was not observed, mainly supply basin. In other side, you can find more precipitation and increase the runoff. So in that case, you can find the reduce of concentration of nutrients. And some ideas exist to use the more drivers to analyze the HAP events, but transboundary condition and scale information are important limitation. Thank you so much.
Thank you, David. Questions from the floor?
Well, that's great presentation. I love it. I have a thought when you use Landsat 8 data, which atmospheric correction algorithm were you applying? Were you using level 2 data from the NASA, or were you applying another algorithm?
I applied NASA algorithm. Yeah, this case was the in this moment that was used. Yeah, in this case we have a plans to use another kind of satellite missions like Sentinel, but we do have enough time to do that. But I hope in the next semester to start to explore this satellite. Okay, thank you so much.
Follow-up question.
Okay.
Not so fast. No, I just, God, I forgot what I was going to ask you. So I noticed the precipitation, there was quite a bit, but then in the last couple of years, like it had dropped and then come back up. And, so maybe it's not just an overall linear increase, but there's a lot of variability there. And I would think there's like a lag in what the lake sees, like maybe algae in this lake are responding to inputs from, say, a year ago or something. Like it's not necessarily cause and effect. Like there could be some latency or delay. I don't know, just what your thoughts are on that.
Okay. In the case of Ouija, yeah, I know the precipitation in that case I did show that is increased. No, but we need to explore more about what is the main or several variable that can affect the algal blooms. Yeah. In this case, oh, can you repeat the question? Sorry, I can do it.
So just trying to look at cause and effect or relationships between precipitation and increase or changes in water quality. The lake can act as a buffer sometimes, and the changes you might not see it in the lake till the following year. Does that make sense or no? But maybe not. I don't.
Yeah, in the case of precipitation, we try to identify these elements are a part of input to increase the algal blooms. Yeah, but maybe the natural process in the lake respond to another kind of variables. For example, the crops around the area, and in a same time, those elements are increase the presence of algae. And another maybe is the regulation, for example. Downstream of the lake, you can find a dam. So it's another element to affect. So there are co-variability of elements to affect the water quality in this lake. So in this condition, we try to identify some elements to give recommendation and improve the making decision from the environmental authorities. How deep it is 2 to 30 meters. It's a shallow.
Thank you. If there's no other questions, we'll move on. Our last speaker of the day, the title is Risk Management Tool for Water Utilities. It's Natalia Rodriguez Alfaro. Is that correct? Close? Of Casa de Agua in Costa Rica. Natalia is an industrial engineer who has dedicated the last years of her career to projects related to strengthening the management and resilience of rural water utilities in Costa Rica.
Well, good afternoon, everyone. We have had an amazing day full of extraordinary presentations. And for me, it's a privilege to be here presenting you on the critical issue, risk management, water risk management. I'm going to present you a risk management tool especially designed for rural water utilities in Costa Rica. We are looking for empower these community organizations to manage risk management in a better way. Well, first of all, I will present you about the context in which this tool emerged, also the methodology that we choose for designing this tool. I'm sorry, I'm hearing myself in Spanish and I'm like, also, what is the tool, exactly the tool, that HIRA tool, and how we use the scientific geospatial information for risk mitigation, and show you some results about the HIRA and the uses that we have today. So first of all, we are in Costa Rica. We know that we have a multi-threat territory. We have climate change. We go from rainfall scarcity to extreme hydrometeorological events, even more frequent and more intense. Also, we have technocean, seismicity, volcanism, the contamination of our fields with agrochemicals that Alexander exposed a few minutes ago. And we are in the middle of a region that has had experienced several events from these tropical storms and hurricanes. We have the Hurricane Otto in 2016. We also have Nate in 2017. And now we are facing the Niño, that for us is up to 35% less of rainfall in some regions. We have an abusive land use for agriculture. And now all these are risks that the rural water utilities must face. What are our rural water utilities? Named ASADAs. Well, there are rural organizations that manage a significant part of our water supply. We are talking about 30% of the water population is provided by these ASADAs. We have around 1,200 ASADAs, but these ASADAs are very different between them. We have some that are serve up to 6,000 subscribers, so a robust ASADA, but there are others that are smaller than with 100 and 300 to 300 subscribers. These are led by neighbors that go around and serve the community with water. And this was a challenge because we needed to design a robust tool that really solve the risk management problem that we have, but that can be applied for any ASADA. So for this, we got an interinstitutional project with all these institutions, led especially with the IIA, that is our national water institution, and also the UNDP. And we were the consultancy that had to solve this problem that we had. So for this, we needed a framework to put all these institutions together, and we decided to use the Sendai framework. This is disaster reduction framework as a global agreement adopted from the United Nations states to guide actions on disaster reduction. This has 4 priorities: understanding risk, strengthening disaster governance. We are talking about ASADA, so we needed them to feel empowered in how to battle this disaster risk, investing in disaster reduction, and also enhancing disaster preparedness for effective response. But the thing that we like it the most of this framework is that they promote risk identification based on local knowledge and also scientific expertise. And so what we did is to design a HIRA that is a tool that has the methodology, a simple Excel file where you can guide the ASADA with the methodology, and also a guide for developing comprehensive risk management plan in ASADAs. This HIRA allows the ASADAs the identifications, evaluation, prioritization, and management of the disaster risk within their system and services. We have 6 modules. The first one is the characterization of the system. That is basically, come ASADAs, let's look at a map of your system. What do you have? What do you have near? Let's see what are your risks. Also, we have a questionnaire of the vulnerability analysis, where we can see the gaps that they need to work with. Also, the threat analysis in the territory, the risk assessment and prioritization, and at the end, we get a risk management plan so they can improve year after year in their risk management for the water utilities. Today, I would like to expose about how the geospatial information help us in this two module, characterization of the system and threat analysis in the territory. So remember that the Sendai framework tells us that you have to use the local knowledge, right? So we asked the Asadas that please let's build our map, because some of them didn't have it. Was the maybe one person that worked for 20 years in the SAD and knows everything about it, but we didn't have it, a document that explained us. So we began with this. And this, can I point here? Yes, these labels, they can identify which risk do they have if they have, for example, cows near the water supply. So it is a risk. What level of risk it represents? A low, medium, or a high risk. So in a simple way, we managed to get that information from the local knowledge. But we had to include the scientific information. So for that, we had a methodology that was built by the Master in Science, Maria Jose Molina, and the engineer Luis Diego Monge, here present, that create a methodology for generating risk index, which incorporate that necessary scientific information, but in a simple way, enough for any SL. So that risk base was based in a level of exposure of a subwater basin for the different threats. We have, let me go. We have landslide, drought, volcanoes eruption, fires, anthropogenic threats. All that information can be given to the ASADA to build and make decisions. So the way they did it is by measuring the level of exposure or the subwater basin, because every ASADA need to know what's about their water basin. So comparing the unit of measurement using a fishnet with sizes of 250 meters, so they can identify the hexagons exposed to each threat relative to the number of hexagons in the watershed. So the hexagons exposed are understood as the footprint of the mapped threat shape pile. This here is the last area of a study that we did last year. Every single point, blue point, is a water supply for different asadas, and the yellow limits are at a different sub-basin. So we needed to include all the threats. What we did is, for example, precipitation. We divided in each fishnet, and so we can understood that as a level of exposure for each sub-basin. So this information was translated to a simple index from 1 to 4, so the asadas can get a number of level of exposure, as simple as that. So this is an example of the drought indicator, but we also did it for the seismic acceleration, for the anthropogenic exposure, and all the threats that we needed to evaluate. Imagine this asada, the asada Sabanilla de Acosta, that knows a little bit of how this works, but then there's a tool that give you the level of risk index for each of these threats. All of these threats, I got a number and a level that can be low, high, too high, so I can take decisions from it. And also, I can get a map, a simple Google Maps, in Google Earth, I mean, where I can identify my water supplies. And if I have, for example, a landfill that is threatening my water supply. also I can go to a better level of exposure and to see, for example, the agriculture that is affecting also my water supplies. All this was translated to decision making, to actions, corrective actions, so the asadas can improve year after year in their risk management for the water supplies. We also had the analysis, the vulnerability analysis that gave us specific corrective actions for each vulnerability, sanitary, operative, management, infrastructure. Also, all the threat analysis that includes, for example, the economic estimation of potential impact. That's what's included in the tool. So for that, they can take decisions about, is this impact risky enough to take decisions, to invest in it, or I can handle it if it comes to me. So at the end, we got some products, the map, the risk map, the comprehensive risk assessment, and the prioritization of actions measures. We got also the action map, the action plan for risk management, including the corrective, preventive, the emergency response, and building continuity. And here in the preventive plan, I may mention that we use some plans of climate change adaptive measures. That is a new, more recently added to the tool. And also a self-assessment result report for water quality seals. Today, the HIRA is accepted as a valid risk management by the national institutions. This was designed by the national institution in Costa Rica that the AIA, but now it's accepted, for example, for the local governments, also for the health ministry, and all the others that come to the asadas and ask, okay, asada, give me your risk management plan, and they don't have a way to do it, you know? So this is a solution for them. It's widely used by many asadas now. Also is a case of study for students in their thesis and undergraduate thesis, and is projected by the idea to be developed into the web-based tool for applications in other countries. So this is the presentation that I have for you today. Thank you very much. I hope you enjoyed.
Thank you. It was really interesting. My question goes a bit in line with, so one big part of the HIRA, as you explained, is the Excel spreadsheet, which makes it pretty simple for them to follow and fill up. The question goes more on this GIS process that goes parallel to some of the analysis, and how is it expected, maybe, or planned in some way, the capacity building so that some of these things can also be done internally by the asadas, and not to have someone externally coming and always having to do to assist them with that process.
Exactly.
And the
Thank you.
challenge that represents.
Good question. Actually, well, in the tool, they got the index as a number, so they can go and see, well, for that row, I have an index of 4. So I will make some measures for some corrective measure for that. But more than that, we aim the asadas to work together, because it's not the same that I work for my little asada that work as a group of all the watershed. So we aim them to, actually, there is a part of the HIRA that says, okay, your neighbors of asadas are these ones. Please work together so you can solve the bigger problems as a group. So in that case is what we propose in the tool. But also there are other methods that are coming up to, especially for the emergencies preparedness and how they can work in case of an emergency. For example, they share resources. Okay, I have some my human resources. I can give it to you so you can have it for your emergency, and we work together. It's a very good. We had very good experiences about that. Yes.
My question is again about the methodology. You have used the hexagonal shapes. Isn't it too old technique? And also you may feel more trouble with using the satellite data with it. So would it not be better to go for a grid, like equal grid, square shape? Then it would be more easy for you even to use further more, compatible satellite data with it. What is your opinion?
Okay, I will ask them for that. But I think that there is well, I will not answer.
Okay, now what's handled. Okay, the idea of the hexagon is because of its geometric properties. It has the ability to better adapt to the different morphologies of that we're trying to study. So as you know, the hexagon is the geometric figure that can encompass the biggest area without the minimum diameter. And when you translate that into a map, it gives you like a better resolution. Yet it poses some challenges because if you're working with satellite data, which has the pixels are square. So, but what we try to do is like to work with a statistical average for every hexagon. So yeah, it's something that we need to keep working. Of course, this tool is hoping to improvements, but so far it's been a great tool for different communities, and hopefully, if not us, other people will continue to work and continue to improve the methodology. Now that I have the microphone, I will also like to take the opportunity to once again invite you. Tomorrow we're having the field trip in which we will be visiting one specific asada in the Valley of Orosi. They have implemented here, so you will have the chance to see how the local communities use these tools in order to improve their water management. And also, it's a pretty beautiful place, so you can get to see a little bit of Costa Rica during your visit here. So hopefully tomorrow will be a very successful and very fruitful field trip where we can all learn and also see a little bit of Costa Rica.
Thank you. Great presentation. I'm just wondering, is there any threshold values to raise the risk and to the communities?
And any pressure values?
Yeah, to inform actually you are of high risk, you should take some measures to control the risk or mitigate the risk.
Well, in terms of water management, each area has different threats. For example, in Cartago, the place that we were mentioned by Alexander, they have a big problem about quality of water quality. And the way that they have to solve that problem is different for them than for other areas in the countries. But the good practices tell us that one of the biggest resources that we have in water management is the community, the associativity from asada to asada. Now we are reinforcing asadas, not just to talk about and be ready to help, but to build an official organization of asadas so they can get, for example, more resources from the state to share with them. And I think that's the better way to solve risk management. I don't know if I answered your question or not.
Thank you. I have a question related to the 4 risk levels that are, as I understood, integrated in an Excel. Does that mean that's a static information that is like based on a general assessment that was done? And how can, for instance, water quality threats be then communicated, because the situation might change depending on the activities upstream? I think the web tool you mentioned would be a great extension, but I think that links also to the previous question, and maybe.
Yeah, the idea of the index is to provide a starting point for these communities to start the assessment. The HIRA tool has a lot of resources, a lot of information that the communities they research and they put that information in. The idea of having this index is like give them like a framework, like a guideline, so they don't start from scratch. So they have like some starting point, like, okay, this is a place that where we have risk of flood or drought or etc. But then after that, the tool is filled with information from the community because they are the ones that know their territory, and they are constantly updating it. So the index is like the starting point, but then the more crucial information is updated by the same Asada on a regular basis. Okay.
Sorry. Shouldn't be asking so many questions here and give the floor to others, but are there any institutions in the country that are feeding information into this? Because I think this could be very powerful if you partner up with water and sanitation agencies and environmental agencies to feed information that can be communicated to the Asadas then, and that can benefit from the activities of the Asadas. Is this something that has been explored? And yeah.
Well, actually, it is a limitation that is an Excel tool, that because it is static, and this index has to be updated in a, I don't know, I think that is like every 5 or 4 years has to be updated. But there are some organizations that are interested in the methodology, but to apply them in their fields. What you are proposing is actually a very good option. So this index can be, for example, imagine that we have our web application now, and they can they can have the inputs in that application. So we can have, in that case, updated information to get using for the asadas. I don't know if I'm explaining, maybe tomorrow we will understand it better, but the asadas are a group of neighbors that fight for the community and the water resources. So this tool and the information, the scientific information given to them, and if it is updated, well, will be an amazing change for their risk management.
Was there any resistance to acceptance of these risk tools from the SADA? Do they think we know our watershed, we know more than you know? And
well, actually, as the start point is, please give us your information. You know everything about your asada. We need to document your local knowledge. So in that point, we gain their trust for telling something. And the scientific information is more as a thank you. I needed this. They are amazed by the maps that they can draw and see all the information and all the layers that they can put. For example, okay, I want to know my I don't know, seismicity layer. Boom, I put it in my map and I see, okay, no, my water supply is in a risk or not. That is not just a simple thing to imagine for ASADA. So if they are not, they accept it with open arms, actually, but they have a limit of capacity to, even if it is a simple Excel tool, sometimes it's difficult for them to operate it.
Me parece bien interesante. Sorry, it was very interesting. The asadas, the boundaries of the asadas are the boundaries of a watershed, right? The geographical boundaries of a watershed. And what about the people who manages those asadas? Do they have certain level of instruction? I mean, some basic technical level of instruction, or are very diverse? For example, this asada has people with certain level of instruction, but the other no.
Well, in some cases, there are asadas that share the same watershed because they're more like small political organizations that are built from the town. Neighbors from the town built the aqueduct and then they began an asada. So there are very different levels of capabilities. For that, the IEA is inviting the asada to get a manager. The managers are the ones that level all the asadas in the same way so they can implement these kind of tools. And in that case, they are our aliados. So, yeah. So I don't know if that answered your question or not. Exactly. As I mentioned before, there are asadas that are like big companies with 6,000 subscribers. You know, they're like bigger than many of the other asadas and work very good. They have their building and their cars and their tractors, you know, that kind of asadas. There and others that have like, I don't know, 100 subscribers, and that's it. And they have to pay for the fontanero. I don't know how to say it in English. And they have to pay the rent and pay the, you know, that's very hard for them. So this tool may help us get to a better level of management that maybe is not available for them in a simple way. Yes. Well, thank you very much.
So I think I'll go ahead and wrap this up or close this session. I want to thank Francisco, David, Natalia for their talks today. As I was listening to all three, I was again trying to rack my brain over what's a common thread between these three talks, because they're all fairly diverse or different talks. But I think in some ways they all discussed the uncertainties we have, or the uncertainties in our measurements, be it the amount of cyanobacteria or the relationships between watershed and water quality, or in this case, risk assessment, you know, how we're trying to get better at, you know, understanding the risk and with the ultimate goal of, you know, we want a safer world. We are interested in ecosystem and human health, and we're hoping these tools will help in that respect. So with that, again, let's give a round of applause to all of our afternoon speakers.